Today we're at Micromethod's office. It's October 19th, 1996, and we're doing a checkout run on this 1795 demo system that TI had put together in 1993. We're running some small demo programs. There are 4 of those. One has to do with text entry, number 2 with temperature conversion from Fahrenheit to Celsius, number 3 a little family budget cellular calculation like a spreadsheet, and then beyond the built-in demos that are pre-programmed, there's also a program mode, and we will get into that, enter some small programs, and see what is displayed on the screen as the programmatic part of this demonstration. There are 3 programs that we will use. One is to test the class of instructions that load a literal byte into a program register. The second is a test of shift right and shift left operations and the effect on flags. And then the third is a little program that generates the Fibonacci series of numbers given the first 2 numbers in the series hard-coded to start the program running. Okay, Don, why don't you turn the machine on? Try not to move it though, it's in a focal arrangement. We expect that it's going to do this vertical shimmy for a minute. Don't turn it off yet, you gotta let the vacuum tubes warm up. That's probably long enough. Off and then back on. I note that on is pulling that slide switch forward. Guess we didn't wait long enough. A little longer. Okay, leave it off for a second. Okay. There we go. Now the contrast control you can play with to see what is the most readable. Steve, is there anything you can suggest? You can pull it into a tighter shot if you like. And you can read it. It says TMX-1795 demo system. 1 text, 2 temperature conversion, 3 sort, 4 spreadsheet, 5 program mode. Of course, I knew what it said, more or less. It's very crisp on the actual screen. White on dark blue.
Let me go back and focus.
And that was better for a second there. There. That's the best I've seen. Okay, let me proceed with, I guess we'll take this in the numeric order of the menu. First demonstrating the little text entry program that you invoke by pushing 1. That's my finger. And then you can enter text. I'm just randomly pushing keys. The text entry demo program also includes being able to backspace, so that last HJ can be removed, and then the very correct VBN entered. That's pretty much it. The cursor keys don't work in text mode.
That allows multiple lines of input.
No. I hit the enter key, and apparently that terminates the or deletes the text that's been entered. So let's go on and see if we can exceed, I suppose, 80 characters. It does wrap on the display and keep on going. So that will conclude the text entry demo. After we hit the escape key, it will go back to the main menu. Go back to the main menu. Okay, we're back at the main menu. We've zoomed the screen so that we can read the characters better. And Don Lockard will show you the temperature conversion demo program.
Okay, we enter the program by using the 2 on the main menu. We see we get a request to input a temperature in Fahrenheit. If we input 50 degrees, that will give us a Celsius temperature of 10. The corresponding temperature in Celsius is 10. At this point, when we go back to the main menu, go back to the conversion program again, and we'll use the value of 22, which is obviously below freezing. And when we do that, we see the answer comes back as a negative 5.6 degrees, demonstrating both that it does negative numbers and partial fractional digits for temperatures. And at this point, we can use an escape or an enter to get back to the menu.
Okay, here we are back at the main menu, and I will demonstrate the sort demo program. We enter the program by typing a 3. It says initializing memory. Now it says enter text, and I will enter some 3-character strings in semi-random order here. UWE, enter, ASD, enter, RTY, enter, ZXC, enter, JKL, enter, IOP, enter, and then you cause the sort to occur by pressing the F1 key. So the A string is followed by the I string, is followed by the J string, is followed by the Q string, is followed by the R string, is followed by the Z string. And at least for this well-behaved set of 3-character strings, the sort worked perfectly. some strings that I typed in, and it worked correctly as indicated by the screen. I want to go back and do that again using a more complex sort problem. Because there is an interesting effect here that doesn't have to do with the chip, but we thought we'd better show it. Again, we're going to enter the sort program by pressing the 3. And I'm going to enter the following strings: H, A, B, H, A, B, C. And I'm going to tell it, well, let's put one more in. B. And I'm going to tell it to sort by pressing the F1. So it behaved correctly again. Let's do this one more time with the same strings but in a different order. H, A, B, B, H, A, B, C. And we're going to tell it to sort by pressing F1. So at this point, even though we entered the same strings, we got a different result. It appears that ABC, a longer string, is sorted to the bottom of this list if you enter in the order I gave.
It was the last string entered, and it came out on the end, instead of being sorted up with the A's like it did in the prior example.
So clearly there's a bug in the sort routine. I don't think this is due to any problem with the chip, but it might be a good idea to figure out what the sort routine is doing. Okay, we're back looking at the main menu. We've adjusted the zoom so that we can demonstrate the family budget, here called a spreadsheet demo. Don will press 4 and we'll get on with it.
Okay, we enter 4 at the main menu to get to the family budget spreadsheet. There is the cursor is positioned at this point on the husband for January, and it's a block right there that's blinking. When we enter values, we can enter up to 4 character values. We use the cursor keys to move, so I'm now moving down from the husband to the wife, and as we did, you can see that the total for the income was calculated and the net for the month was calculated. So we can enter values for different ones. The maximum number of characters that you can input is 4. When you try to enter the 5th one, it cleared the screen and went back to 0. If I use all 9s, okay, when I entered a 1 followed by zeros and went to 10,000 and went to 0, all 9s stops at all 9s. So that is a the way it works, the backspace key deletes a character so you can adjust the value. And I can move down to the other value. And each time I move off of a field, you can see that the total and the net are being recalculated and displayed on the screen. I'm now sitting at other for February, and we can have some other income for February. If I come down to expenses and I have a $200 rent expense, but I only have $66 income, you can see we have a negative net income for the month. So the net value down below will display negative numbers indicating that you're spending more than you're receiving. We're taking the values in the top half, calculating a total, taking values on the bottom half, calculating a total expenses, and then subtracting the income total from the expenses total to get a net for the month. And you use the cursor to move left or right. One of my curiosity points is if I try to go left off of from January, I end up in December, which is off the screen. If I go right out of December, then I wrap back to January, which lets you continue month by month, and you have a last 12-month view since you don't have a year associated with it.
Don, do you want to show what happens when you enter numbers that sum to more than 4 nines?
Yes. Let's move our cursor over to March and go up to the husband. We will enter 2,500 for each of these fields, which obviously when we add 4 of them together, we're going to get 10,000. But as we move off the other, it displays 4 stars indicating that we've exceeded the 4-digit field, much like any PC spreadsheet would do when you've exceeded the output field. If we move back up to other, we will delete the 500 and make it 499. So if we didn't make it, I went too far. Well, let's make it 2499. And then when we come down, we end up with 4 nines. So that's the maximum capacity, is a 4-digit output for the totals.
So that pretty well shows you the family budget demo program, and that includes negative numbers and up to 4 digits entered, and cellular structure like a spreadsheet.
And we're going to go back to the main menu.
Yes.
We'll do that with an escape. It asks us, do we really want to do that? And we'll answer yes.
Okay, we're back at the main menu. Off to the right, you can see the 1, 2, 3, 4, and off to the right, there's a 5th choice called Program Mode. We can't show it to you because we need this particular screen focus for the next example. What I'm going to do is press 5 to get into the program mode, and you'll see what I mean. We're now in a editor that allows you to enter some instructions that will be executed, and the results returned to the display when we are through entering. So what I'm going to do is see how a particular class of instructions, the load literal instructions, behaves. I'm going to test all 8 of them. So first, there's load A with, I'll just choose a constant 1. The octal code for that instruction is 06. And the cursor's moved to byte 2, and so it's asking for the literal to go with that. So the first line now reads load literal 01. There is no third byte. This editor wants me to remember that, so I now hit a return to get to the next instruction. And you notice the program counter has advanced to from IC00, 1C00 to 1C02. And the next load literal that I'm going to enter is load B, which is the code 0E. I hit an O. 0E works better. And I'll put a 2, the constant 2, in the B register. And again, I have to hit enter to get to the next instruction at 1C04. The next is load C with a constant 3. So in hex, that's 1603. Return. Then load D with a 4. That's 1E04. Enter. Then load E with a 5. That's 2605. Enter. Then load H with a 6. That's 2E06. Enter. Then load L, the final register, with a 7. That's 3607. One enter prepares for a next instruction. At this point, hitting enter will switch us to the simulated debug mode here. So now we're looking at the debug mode, which was the reason for the screen focus, so you can just barely see all of the registers with from A in the middle of the screen to L at the extreme right of the screen. All of the registers have been initialized to by the debugger to the value 0. And by hitting the space bar, I can execute the instructions. You can see the 0601 that I typed in is the instruction. I'm hitting the space bar to execute that, and now you can see that it did indeed put a 1 in the A register. And it is prepared now to execute the second instruction, which puts a 2 in the B register, and the 1, of course, is still there in the A register. And then as we continue, there's C equals 3, D equals 4, E equals 5, H equals 6, and L equals 7. So we have now verified that all 8 of the load literal instructions do in fact function correctly. The way the debugger works, it will now see an instruction 00, and I believe that's a halt code. In any event, it's going to, as I try to execute it, it's going to exit this screen and go back to the main menu. So here we are back at the main menu, and you can see that the 5th choice on the main menu is program mod, or actually program mode. Again, we're choosing the screen size carefully to try to show you what is interesting on this example. Don is going to show you the operation of shift left and shift right instructions and the effect on registers and flags.
Okay, we'll start by entering program mode by typing a 5. Again, we're back at the program enter position where at address 1C00, and we're ready to enter our instructions. We're going to start by loading A with a value. So that's a hex of a 06, and we chose a value of 55, which is every other bit off and then on in the register. Then what we're going to do is shift the contents of the A register in a circular manner to the right so that the lowest bit shifts out of the A register and back into the top end of the A register, with the carry flag being indicating whether the bit is a 0 or 1. So an SRC instruction has got the hex code of a 0A, and it has no second byte required, and we're going to enter 5 of those so that we can just rotate the data back and forth or around through the register and see the effect. And so we've entered 4 of them. We're now at location 6, and we'll enter our 5th one. At location 7, we're going to change the direction. Instead of going to the right, we'll start doing a shift to the left, still setting the carry indicator, and this is a 02 instruction. And again, it has no additional bytes required, so we will enter 5 of those. And one more, and we have completed the program. And so now, at having created instructions down to 0B, we're ready to execute them, and we'll press enter to get into execution mode. We now see that the registers have been initialized to all zeros, with the Z flag being set to a 1, and we're ready to execute our load A with a 55. When we hit the space bar to execute that, we can see the contents of the A register has changed to a 55, and that is the only no indicator flags change. We still have a carry of 0. We have a 1 in the Z, which
is correct. It indicates that the A register,
it did not change.
Maybe there's a question there.
The question is, does a load instruction change the flag bit?
Yes, we'll have to look at the intended instruction set.
So as we shift to the right, we would expect the A register to change from a 5-5, and we would expect some flags to change, and we would do that. And when we shift one character, the A changed from a 5-5 to an AA.
And the carry is set to a 1.
Carry set to the 1. We shifted to the right. We took the low order bit of the second 5, shifted it out, and in setting the carry indicator, and shifted it back into the top. So now we have an A, which is the first bit turned on and every other bit off and back on again. When we do it again, the next iteration, we would expect the A register to go back to 5-5, and it did.
And the carry went back to a 0.
Because this time we shifted out a 0, and we are not driving the 0 flag with a shift. It does not. Obviously, it's not driving that flag. And when we do it the next time, we go back to an AA, and the carry bit turned back on as expected. One more time, and it turns off. And our last time of shifting to the right, we go back to an AA with the carry indicator on. and this entire time the Z flag has stayed stable at, is always 1. The sign and the parity flags have both stayed at 0. And when we shift to the left, we expect the same thing to happen to the A register. That is, we have shifted the bit out of the top end and into the bottom, so we now have a 5-5, and the carry flag is on again because we still turned it on. And when we execute this additional times, the carry flag gets turned off, and when we have an AA, we go back to a 5-5, the carry flag turned on. We go to an AA with the carry flag turned off. We go back to a 5-5 with the carry flag turned on, and our next instruction is the end of program, a 0 instruction. So when we hit the space bar, we'll go back to the main menu.
Okay, here we are at the main menu, zoomed in corresponding to what I need to show you the next demo program. We're going to go into the program mode and type in 7 instructions that I wrote to generate a Fibonacci series. And the presumption is that the first 2 numbers in the series are entered into the program as literals, and then the program is in charge of generating the numbers in the series after the first 2. I think I'll choose 1 and 3 as the first 2 numbers in the series. So let's go on ahead and get into program mode, and I'm going to put the constant 1 in the B register. The code for that is 0E01. Enter. I have to say enter to myself or I forget it. I'm going to put the constant 3 in the C register. The code for that is 1603. Enter. Then I've got a load instruction moving B to A. The code for that is C1. Then I've got an add ADC. It adds the C register to the accumulator. The code for that is 82. Enter. Then I've got a load putting the contents of C in the B register. The code for that is CA. Enter. Then I've got another move, LCA, which puts the contents of the A register into the C register. The code for that is D0. And then I've got a jump. I need to enter a jump that goes back to this instruction, which is the load B into A instruction right there. So the code for that, jump code, is 44, unconditional, and the address is entered Little Endian, so 041C. And that, I think, is the correct program according to what I typed. Now we'll find out if it's the correct program according to the 1795. So this enter completes that instruction. Second enter sets me up to check out if the program is working correctly. If the program is working correctly, the series corresponding to first 2 numbers being 1 and 3 will start appearing in the A register at the I1C05 address. So we'll go on ahead and space through the first loads. You can see the 1 is now in the B register, the 3 is in the C register. CO4 is another load.
Move B to A.
And then ICO5 is the instruction 82, which is the add, and I think that will create a 4 in the A register. Sure enough, there's the 4. Then we just keep doing this, and the next number that should appear in the A register is a 7 right there. So we now have the second, or the fourth number in the Fibonacci series, starting with 1, 3. And we can keep doing this for a while until we've executed a total of 256 bytes, at which point the instruction buffer in the program will overflow and probably the program will stop. I'm not sure what happens when we run out of the screen before we run out of the instruction buffer. The next number in the series should appear with this instruction in the A register. There should be an 11. Uh-oh.
That would be fine if
I'm
we're
sorry.
doing it octal, but
Yeah,
hex.
11 I wrote down in decimal. I mean 0B. So it's correct. It just speaks in a different tongue. The next one, Don, maybe you can calculate it for me, should be 18. Whatever the hex is for 18. Steve, do you want to try to follow me down the screen? Let Don do the calculation before I hit enter.
One. Let's see. 1, 3. You
Huh.
have to. Well, you.
Oh,
You have to.
I'm not done yet.
Not done yet.
I
12.
got 1, 2.
1, 2. That's correct.
So the 1795 in this instance was faster than Don. Okay, let's keep going if this, as long as this keeps going. The next one should be, let's see, 11 and 18, 29, decimal, whatever that is, hex. Can you follow me, Steve?
1E.
I'm at the bottom of the screen.
So I think it goes into scroll mode at this point.
I think it does. Nope, I think we lost it.
Or is it on the top of the screen?
Yeah, the cursor's up there on the second line.
We'll go back to the top of the screen when we roll.
Oh, I see. We go, if you scroll back up, you can see that the answer is there. It is a 1D. Is that what you said?
Yes.
Okay. So the results wrapped around and came back up to here, and there's our 1D. So I'm going to keep on executing, and I suspect pretty soon we're going to run out of the 256 bytes. .2F is apparently the next number in the series, which would be 29 and 18.
Mm-hmm.
And 4C is the next number in the string. Accidentally, the number of lines on the screen divided by the number of instructions in the loop
Roll.
must be an integer. And 7B is apparently the next number in the string. Oh no, what is that?
Yes, 7B is what you...
Okay. And then C7 after that. It occurs to me there's another way to overflow this program. Of course, we've only got 1 byte, which is maximum value 256, 255. So I wonder if we run out of that 256 before we run out of the instruction 256.
And now we're at the top of the screen, aren't we?
I don't know what happened.
We obviously have gone out of the... We're lost.
Okay, we exceeded the buffer is what you're saying.
Yes.
Okay. So in any event, we got several Fibonacci's calculated, and that's the end of this demo. I think I'll try to escape with the escape key, which worked okay. Here I am again with my notes about the checkout run, and I just want to summarize what we did. In trying the text entry program, we verified that you could indeed enter text. We found out that if you press the enter key, that ends the session of entering text. We did find out that if you keep on typing beyond the 80 character width of the screen, that the text wraps to the next line. Then we went on to the number 2 program, which is a temperature conversion, Fahrenheit to centigrade. We tried a number of 50 degrees that converted to 10 degrees Celsius, and we also tried 22 degrees that converts to a negative Celsius value that I don't remember. But in any event, the program can handle negative Celsius output and fractional output, 1-digit fractional. The next thing we demonstrated was the sort program. The sort program has an aspect that's a little bit user hostile. We figured out after we ran this series of sorts that what it's doing depends on where the cursor is just before you press the F1 to cause the start. If the cursor is on the same line as the last string that's to be sorted, that string will be ignored. On the other hand, if you terminate the last string by hitting the enter key and then press the F1 to cause the sort, the last string will be sorted. We believe that's the rule. Don Lockhart is going to look at the code and verify that that is in fact what's happening. Then we did a little budget demonstration program, and in that case we found out that if you enter values in the cells that add to more than 99.99, the program returns 4 stars, star, 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 star. So it's a modern overflow. We also found that the cursor keys can wrap so that if you keep hitting the right cursor and go past December, you're back in January. At that point, we ran the load literal program and verified that all of the loads, load A, load B, load C, and all the way through load L, do in fact behave properly. And that was important to know because some chips in the beginning, some of the very first chips produced apparently may have had a problem with these type of instructions. The next program we tried was the shift right and shift left programs or instructions, and we verified that they did as expected with the A register alternately holding AA and 5-5 as the bits in those two constants are rotated, one to convert an A into a 5 and another to convert 5 into an A. I was startled a little bit about the 0 flag that appeared to be on, but I checked the manual, and the 0 sign and parity flags are not affected by this type of instruction. That is, the program holds a load instruction and a number of shift instructions, and the 0 sign and parity flags are defined to ignore those type of commands. So it did perform correctly. Lastly, we entered and I'm relieved to say correctly ran the Fibonacci code that I generated, and the program generated the Fibonacci series that starts with the constant 1 and the constant 3, the program generating the successive values 4, 7, 11, 18, 29, and so forth. We deliberately kept running that program through one loop per new value in the series in order to overflow the capability of the program mode. The way program mode works is it unrolls those loops and puts the target instructions of the jump and instructions after the jump into an instruction buffer, and the unrolled sequence of instructions cannot exceed 256 bytes, the size of the buffer, the instruction buffer that it is pretending to execute. So we apparently achieved that goal, and at some point with I think the constant at the time was 4C, the last value generated by the series before we exceeded the buffer capacity, I believe was 4C. And at that point, the program misbehaved in a way that we don't fully understand, but again, the root cause has to do with the program buffer. So that concludes our checkout run of the 1795 demo system that seems to be running just fine, and looks like it's having no problems. Thank you.